So let's now dive in and talk a little bit about this issue of races and reliability, because this has to do with parallel correctness. So parallel correctness, as I mentioned, you can test using the Cilk screen race detector. So the idea is you produce your binary as before, and what you do now is run it with regression tests through the race detector. What the race detector does is it says it takes some input, runs the program on it, and tells you whether there's any possibility that the execution of this program would differ from that of the serial execution. Okay? So if it does differ, then what you have is what's called a determinacy race. Okay? A determinacy race occurs when you have two logically parallel instructions that access the same memory location, and at least one of the instructions performs a write. Okay, so they've got to be parallel. So if they're in series, no race. They've got to be parallel. If they're both doing reads, no problem. But if one's reading and one's writing, or if they're both writing, then you have a determinacy race. So here's an example. So here what we've done is we have a little piece of program where we set x to 0, and now we do a Cilk for that has exactly 2 iterations, each iteration incrementing x. And then at the end we assert that x is equal to 2. Now if you ran this on a single, if you ran the serialization of this, indeed x is always going to be 2. Because it runs through and it increments for the one iteration, increments for the second. When we run this in parallel, we have a determinacy race. So here's the way to sort of understand it. We can understand the flow of this by taking a look at the first statement here. X is equal to 0. So let me call that A. And now we create 2 iterations that are operating in parallel, each of which is x, incrementing x. So here's this one and this one. I'll call those B and C. And then finally, once those are done, we assert that x is equal to 2 at the bottom here. Okay? So this sort of gives it, this is what's called a dependency graph, and it illustrates the parallel flow of the program. Okay? So first we do this, then we do these 2 things in parallel, and then we do the assertion. Now to understand the data race the more carefully here, okay, the determinacy race more carefully, we need to really break down what's going on in B and C here. Okay? And so the idea here is that those instructions to increment a variable, in fact, is not done as one step. What's done is that the value of x is read out of memory into a register in the processor. Then the register is incremented, and that is done as a single operation. And then the value is stored back into the memory. Okay? Now the problem that you get into when you actually execute this is if the execution order, because of the fact that these things are going in parallel, ends up interleaving these instructions. So for example, suppose that we execute steps 1, 2, and 3. So we do this one first, then we do this one, and then we do this one. So at this point we've read x, okay, 0. Register 1 now contains the value of 1. If we now go and execute these 3, well, register 2 now gets the value of 0 because x hasn't been written back here. And it basically gets updated to the value 1. And now, in this case, it sets x to be the value in register 2, which is 1. Well, likewise over here, this guy is going to set it to 1. And then this assertion at the end is going to fail because x is going to be 1. It was written 1 twice. Okay? And so there's been a lost update because we have 2 guys trying to write, and one of them got the value, they both got the value 0 rather than one getting the value 0 and the other getting the value 1. So this kind of problem occurs, and there are different types of races that occur. One is called a read race and one is called a write race. So suppose that you have an instruction A and an instruction B, both accessing a location X. And suppose that A is parallel to B. Okay? then if they're both doing reads, there's no race. If one's doing a read and then the other's doing a write, we have a read race, or vice versa. What happens in a read race is that whether the thread A sees the value that B writes before or after the write is going to change the behavior for A. And that's why there's a determinacy race. That's why it may not operate the same as you have in a serial execution. Okay? The write-write race, which is the example we saw on the last page, is when you have two guys writing and now there could be a lost update. So that somebody subsequently coming may see something different depending upon which one got there first. Okay? So we say that two sections of code are independent if they have no determinacy races between them. So I have two blocks of code, no races between them, they're independent. And so the goal when you're parallelizing things is that you want to make things operate independently because you want to preserve as much as possible your serial semantics. Okay, so to avoid races, the first thing is that all the iterations of the Cilk 4 should be independent. Okay, so you want to make sure all the iterations are doing different things, operating on different portions of memory. If you have a Cilk spawn, so here's an example here, okay, from the quicksort example, then what you want to make sure is that from the point of the spawn up until the sync, okay, that all the code that's executed by the parent, including any calls it may make or whatever, are independent from all the calls and so forth that might be made by the thing that's spawned. Okay? So that's how you make sure that those are independent. Okay? And then, of course, I should mention that the arguments to a spawn function are evaluated in the parent before the spawn occurs. So, for example, begin and middle are evaluated before you do the spawn. And then if, for example, we had spawned the second thing, the begin plus 1 would be calculated in the max before the spawn is actually done. So the idea is that if you do get it wrong, that's what silkscreen is there for, to catch those kinds of errors. Because it's not always easy. You may look and say, hey, these two things look like they're operating in parallel, but gee, somewhere down there in the guts of these functions that I've spawned off, there may be some access to some variable that you didn't realize. Okay, and silkscreen then will pick those up. So silkscreen runs off the binary executable, and in Visual Studio, the way that you do it is you go to the Tools menu and you say Run under the silkscreen race detector. There's a tendency for people to look at the Debug menu. It's not under the Debug menu because that's really all the Microsoft stuff. It's under the Tools menu, even though this is, if you will, a debugging tool. Okay? The results appear in the Visual Studio output window. And the results there are now sensitive, and if you double-click on a line of output, it will bring you to the particular line of source code where the race occurs. So as you mentioned, for silkscreen, for given input, it mathematically guarantees to localize a race if there exists an execution that could produce different results from the serial execution. Okay, so it's guaranteed to find those races. And I should say it runs about 20 times slower than real time. So it turns out that for most debugging, people tend to run the race detector on smaller inputs than you would do for regression testing a large application. And it turns out that's generally sufficient because you don't really have very much parallelism. It turns out testing serial correctness is far harder than testing parallel correctness when you have the silkscreen tool. Okay? And it currently uses about 5 times the memory, but we're working on that so that so if you have a large application right now, you may blow out memory, but we're working on that, and we'll have it using far less memory in the future, so that you can run a full 32-bit application and use all the memory space and still be able to run silkscreen. Okay, so that's great in theory, but the question is what happens in practice when you actually want to cope with real code.